Um, we were doing in previous modules, actually, I think it was module 3 on linear systems. Quick review. You start with a physical system, you come up with a math model, which was differential equations in our case. And using Laplace transform, we came up with this thing called the transfer function. And from there, we were off to the races. Look at the poles, look at the mode functions, the impulse response, the response to any input, basically, the frequency analysis, all kinds of wonderful things, wonderful tools. But this all started with a model with a single scalar input and a single scalar output, y. That was all called classical analysis. Now we're going to get into state space. So let's talk about state space. We could have defined a couple of intermediate variables, x1 and x2. Say x1 is y, which was the position of this card, and x2 is y dot, the time derivative or the velocity of this card. And if you take the derivative of x2, which is y dot, that's y double dot, that's the acceleration. Use the F equals ma math model. You could write this thing. Now we have everything in terms of x's. So we could write this matrix equation involving x's. x1 dot and x2 dot, with this little vector of derivatives, this vector of state variables. Here is a matrix. Here's another matrix. Here's the input. And if we're interested in the output being position, we have a way to express, excuse me, express the output in matrix terms. We call these x1 and x2, this little vector here, that is the state vector. In this case, it means position and velocity. Those are our state variables. And in matrix formulation, it has this basic structure. We're going to add this other thing to the measurement model or the measurement equation. So either one of these is good enough to get started with. Here's kind of where we're going to end up. And now the u, the x, and the z, and the y could all be vectors. We could have multiple inputs and multiple outputs. The F, the G, and the H are matrices. Everything's appropriately sized. So we'll talk about how do you deal with this guy, or these matrix equations, matrix differential equations. So I'll quickly get into that. Right after this, one more thing to add. We can now handle more complicated systems. Here's a system of two cards. It ends up having more state variables and bigger matrices, but it still has the same basic structure, state space structure. And we could have multiple outputs. So in this case, I guess we're interested in the position and velocity only of the second card. We could have put another force on the first card and two inputs. We could have multiple inputs and multiple outputs. And I worked with some navigation applications, and we had state vectors that were more than 40 state variables, 40 individual state variables. So these things can get big, and we have a sort of common way to deal with them, or we will as soon as I tell you about it. But if you can see, it's much more generalized than what we started out with classical analysis. By the way, this is called modern analysis, even though it goes back to the 60s. Once we start dealing with this sort of matrix structure, and we're going to deal a lot more with computers, if you, well, I won't get into that here. First, let's go. Okay, we want to start being able to solve at least this equation. Okay, let's see about this guy. And I first want to introduce, what does this thing mean? E to the A, where A is a matrix, in fact, a square matrix. E to the X, where X was a scalar, and this, I guess, Taylor series expansion, we could define E to the X this way. So we're going to define our matrix E to the A this way. Okay? And there's a couple reasons why I'm doing this, but later in the course, we might use this to approximate what this guy is. Might lop it off after the second or third term. Close enough. That's later in the course. And there's some features of that. I don't want to go through all this. This is one big result. You take the derivative of that little guy, and it acts just like it does in the scalar case. You just bring down the exponent. Either pre-multiply it or post-multiply. This is a matrix, by the way. I is the identity matrix. A is a matrix. So this guy is going to be a matrix. So what? Let's first solve the homogeneous equation where F is a constant. This guy. We're given some initial condition. Convince yourself that this thing, e to the matrix F times this difference in time, times your initial condition, if you plug that in for X, it satisfies this guy. You'll get back your initial condition, and it satisfies this equation. That's what these two lines tell you. So that this, or this right side, is the solution. What if we solved it using Laplace transforms? Go back up here. We have S times the Laplace transform of X, which would now be the A vector, minus this initial condition. That's the way Laplace transforms work. And on the right side, you have F times the Laplace transform of X. You got a little bit of algebra. You have the solution for X in the Laplace domain. If you take the inverse Laplace transform, you have the solution in the time domain. So that there's a theorem, I guess, somewhere that says the solution to this equation is unique, which here is telling us that this solution is the same as this thing, which means we have a way to compute this e to the f business. We could do it using Laplace transforms. That's when the f is constant. What about when it's not homogeneous? What about when you do have an input here on the right? Well, let's call this input GU. We'll call it R for a minute. Use Laplace transforms again. I'm not going to go through the derivation step by step. I just want to outline it for you. You get, this is your total solution, for F being a constant. Here was our solution for the homogeneous part, and here's the solution because it has an input. It's just the sum of the two. You kind of think of it as the output due to the initial conditions and the output due to the external forcing function, the input. And those two things just add. We're going to start calling this thing, we're going to start giving it a special name. Well, let me get to that on the next chart. It seems like it shouldn't take this long, but that solution on the previous page starts from 0. From time equals 0, we can find the solution in any later time. But it turns out you can go from any initial time, not necessarily time equals 0, up to any other time after that. And here is that general solution. Okay, now we're going to start calling this thing, giving it a name. State transition matrix, and we're going to give it its own notation, it's phi. So that here's another way, this is just another way to express what we just expressed. Where what is this transition matrix? This e to the f business, which is also this inverse Laplace transform. So here's kind of a summary of the state equations. Here was a state equation. We didn't get into the measurement equation. This is just a state equation, which that first big thing, matrix equation in the state space format. Here was the equation. Here's the state transition matrix, and here's the solution for the state at any time t2, if you know what it was at time t1, and the input over that time window, time period, t1. This might not look fun to deal with yet, but we're getting somewhere. That's as far as I'll get in this first video. But a big place we want to get to next is the discrete state space. I'll talk about that in another video and why we're even go there.